In this video, we're going to look at how we developed integrals to compute areas, and then we're going to take a look at that same process with a new direction or from a new perspective. Let's start with what we know already. We're asked to write the integral that represents the area under the graph of y equals x squared between x equals 0 and x equals 2. Well, that is exactly what we mean by an integral from 0 to 2 of the function x squared dx. Once we have that integral, we can use the fundamental theorem of calculus to evaluate it. We have the integral of x squared with respect to x. We take the antiderivative of the x squared. That gives us x cubed over 3. And we evaluate that at 2 and 0. And that's going to give us 8/3 2 cubed over 3 minus 0 over 3, or 8/3 square units. Now we're going to take a step back and revisit, where did this integral come from? Here's the graph of y equals x squared. Here's the interval from 0 to 2. And if we look at the integral that we created, it had a source which was looking at a sum of x values. I'll put little subscript i's, because what we did is we divided this interval up into subintervals, each labeled with some x value. And we then counted those values squared, which gave us the heights of rectangles. And we multiplied each of those heights by a width. And that corresponded to a rectangle like this. We then repeated that over and over and over again and built more and more rectangles. And with those rectangles all together, we covered the area we were talking about. The transition from that sum idea to the integral idea was taking a limit, either as the intervals got smaller and smaller, so the width went to 0, or as the number of intervals went to infinity. So what we would have here is a little counter counting how many rectangles we're using, and as that number of rectangles got bigger, the intervals get smaller at the same time, and it led to the integral form. What we're going to explore now is how that same area can be constructed using horizontal rectangles. In principle, there's no reason why this rectangle is more useful than this rectangle here, or a series of rectangles that are laid out horizontally. We would have the same coverage of the area we want, and we can talk about heights and widths, so that's all the same kind of technology. We're just taking this area and dividing it up in a new way. What would that sum look like? Well, you take I equals 1 to n, and we would have I would order it this way, and we'll see why in a second, widths times heights. Because in this case here, the heights are all going to be a small increment in y values. We're taking a y value and going up a little bit, taking the next y value up a little bit. So the heights would be given to us as delta y values. So that's different from before, where we had rectangles that had small widths. Now what about the widths? Well, for each of these rectangles, we can talk about this span in this direction here, and that's where it gets a little more interesting. Let's go to the next slide and see if we can figure out what that width in question marks here is, because that's the only missing ingredient to building a new form of integral to get the same area from a different perspective. Here's our diagram again. Here's a sample rectangle, and so we can imagine that this is the y value where we're building this rectangle. We talked about the height of this rectangle being delta y. And then the question is, what is the width? How far is it from here to here? Take a look at the options in the table below. Think about it for a moment or two, pause the video, and we'll come back and check in. All right, let's do a quick comparison here with what we did before. When we had the parabola like this, and we took a height of a rectangle, it was a y value. I'm going to generalize this from what we did before. We had a high y value, and then we had a 0 value down here. So in that scenario, our height was equal to a large y value minus, well, this is really just a y low value. It's a distance. So we take the end minus the start, or we take the high minus the low. That same argument applies here, except both of these things are going to be more interesting than the scenario here. This had a nice 0 value. But the distance here, this width, is simply one x-coordinate minus another x-coordinate. And if we look carefully at any one of the rectangles, so we want to keep this general, the x high is always going to be this 2. The last point in each rectangle is always going to be 2. 2. If I build another rectangle up here, the final x value is going to be 2 again. More challenging is the low value. That could be here when y is up near 4. It'll be here when y is around 1.5. It'll be here when y is 0.5. So x low depends on the y coordinate. Well, what's that relationship? What we need is the x low on, well, this curve. This is the curve y equals x squared. Well, if I'm looking for the x value, there's the x value. Let's just solve for that. We're going to get positive root y. We're in this range here, where the x value is always going to be above 0. And so this is, let's slide in the low here, our x low. We have a relationship that defines where the low point is on each of these rectangles. And remember, low for x's is more to the left. That's the important direction we're considering if we're talking about widths. And if we put this together, we have the end of the interval is always 2. The start of the interval is always at root y. And so this width is going to equal the x high minus the x low. And that is going to equal 2 minus root y, giving us the answer here, C. At any point, if you ask if y is 0, how long would a rectangle be at height 0? That'd be 2. Perfect. That matches that distance there perfectly. When y gets up to 4, how long a rectangle is there? Well, it's 0 length, but that's exactly what this formula would generate as well. Square root of 4, our y value is 2. 2 minus 2 is 0. And we can check that at all the values up to the peak, starting at y equals 0. With that, we're ready to build a new integral that represents this total area under the curve, just divided up or sliced up with this horizontal rectangle construction instead of vertical ones. Let's do that here. Our total area is going to equal adding up widths times heights. And we know where this goes next. The widths we just found was 2 minus square root of y. The heights were all delta y's, and we had a sum of those. Technically, these would be approximations. The exact total area is what we get using an integral. So we just construct the integral that comes out of this. Instead of a sum, we use an integral. Instead of using delta y, we use dy. This is where we take the limit as delta y gets smaller and smaller and smaller. But this remains the same. The width of each of those rectangles would still be 2 times the square root of y. And then the boundaries are what we need last. If we're taking all these slices, the first slice is going to occur at y equals 0. That's the lowest y value. we're going to slice, 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 and stop here, and that corresponds to a height of y equals 4. Now this looks very different than the integral we had earlier, which was the integral from 0 to 2 of x squared dx. But they represent, through the guise of this picture here, exactly the same region on the plane. What we should find then is that the value of this is also equal to the value of this, and we're going to confirm that in just a moment. If we integrate a 2 by itself and y is our variable, you have to be consistent with your variables here, we're going to get 2y. This is y to the 1/2. When we integrate it, we're going to add 1 to the power. That gives us 3/2. And then we're going to divide by the new power, which is also 3/2. And we'll evaluate that between the points 4 and 0. We then plug in the values. We're going to have 2 times 4 is 8. And the 3/2 becomes a 2/3 if we write it in the numerator. The y to the 3/2, let's write that as 4 to the 3/2 for a moment. That is what we get by subbing in the 4 into the first and second terms here. Then we also subtract off what we get from subbing in 0 and 0. Well, that's just 0 and 0 here. Well, we're close. We just need to evaluate this. You can use your calculator if you like, or you can think of this 4 and the 1/2 power. That'll be 2 because it's the square root of 4. If we end up with 2 cubed, that'll be 8. And so we end up with 8 minus 2 times 8 over 3, or 16/3. Well, that's 24/3 minus 16/3. And that is exactly equal to 8/3 over all. And we confirm that was what we found earlier for the same region defined with vertical rectangles, the integral of x squared from x equals 0 to x equals 2. And so we get a confirmation that whichever way we subdivide this region, whether it's horizontal slices leading to this form here, or vertical slices leading to this form here, we still obtain the same area. What we've done, though, is liberate ourselves from the idea that everything has to be vertical, that everything has to be relative to an axis. We can now take the slicing approach and apply it in many other ways and to many other problems.